Great. Our next talk is from Justin Wilson from Not So Far Away at Louisiana State University. And he's going to be telling us about order and universality in both hybrid and adaptive quantum dynamics.
All right, thank you, everyone. And thank you to the organizers for allowing me the opportunity to speak here. So my title is a bit broad. I actually tried to put too much into the abstract given the time. So I'm going to mostly focus on the adaptive quantum dynamics part of this. And this will be based on two works which are on the archive. One is this work here, and you can see. So one is on this work here, which is simulating some controlled phase transition, which I'll talk about on an IBM quantum computer, and the other is sort of exploring this universality kind of in its most general sense. So I'll describe what I mean by that as we go. Okay, great. So first, my collaborators. So this is the cast of people for both projects separately, and so for the IBM stuff, these wonderful people here, and for the for what will be related to an inverted harmonic oscillator, and in particular some 2D quantum maps. These people here. I do want to acknowledge also that in the course of this project, very tragically, Barbara Jones did pass away. So let's jump into it. So I'd say that we're kind of now like moving a little bit past the NISQ era, the noisy intermediate quantum era, to the early fault tolerant era, in particular because we now have a bunch of platforms where mid-circuit measurements are coming online. I think Quantinium is a big pusher of this. So this is good because now we can actually do things that are closer to what you would see for like quantum error correction. Not fully there, but definitely more on the path than even a few years ago. So this is just a couple of the just a small smattering of papers that have been about this. So like within this, we have adaptive quantum circuits. So when you have these measurement outcomes, you can then take them and you can feed them back into your system and do something, either a correction, or maybe you want to like just have some unitary that's conditional on those measurement outcomes. And so the big idea is that you have these unitary dynamics, local measurements and feedbacks, and now you can do things using this like state preparation, quantum error correction, or really start to look at even some many body physics and consider this kind of a new paradigm for non-equilibrium phases and criticality, kind of like Drew talked about in the last talk. So the constituents for us will mostly be adversarial unitary. So these will actually be giving us some chaotic mixing dynamics. And on top of that, we'll have measurement and feedback, which will control the dynamics onto a target state or a target trajectory of the dynamics. And the big thing that we'll be really discussing is related to dark state control or absorbing state criticality. So whenever you have within your dynamics a state which isn't going to actually change, a dark state, then we'll be pushing onto states that are kind of, at least in principle, kind of like that. And just a smattering of some of the early references that we're doing this in this context. So the classical inspiration for us is actually the stochastic control of chaos. So this actually came from one of like this very early set of papers in starting in 1996, and here's one of them in 97 from the same authors. And this is really to take some chaotic dynamics, classical dynamics, and to control them onto unstable periodic orbits. And so the rough idea is, as the dynamics go along, with probability 1 minus p, you do some chaotic map, which kicks the system around. Here I have the kick top, And all these points are the chaotic dynamics of the top being kicked to different points in phase space. And with probability P, you come in and you perform some control action, which is going to push you close to a periodic orbit. So in particular, say I want to target, this is a bit of a cartoon because usually we're not considering orbits in a mixed phase space, we're considering them in the actual chaotic space, but this actually gives like the idea. You have some periodic orbit here, which is unstable. And we have some dynamics where you start off, say, over here at this point. The chaotic dynamics then pushes this point around to 2 and then 3. And then with some probability, we do our control action. And for our control action, you have to figure out where your point is. So you measure it, a classical measurement, so it doesn't do much, right? And then you perform a control action, which will then push you just a little bit closer to your periodic orbit. And so the thing that they found in these early papers is that this actually exhibits some properties very much like a phase transition, whereas a function of this P, like how much you're actually doing this control operation, you get pushed, you actually turn your unstable periodic orbit into a global attractor, and you get pulled onto it. So that's sort of our inspiration. And in order to do this quantum mechanically, we have to think about how we're going to do the control operation. So we have some chaotic dynamics going on, but now, yeah, So the motivation is that we're trying to like we have like a target state or whatnot that we want to prepare, and that is being acted upon by some unitary dynamics which are trying to like kick you off of it, and so we're trying to put into the dynamics something which is going to like pull us onto our target state that we actually care about. So our periodic orbit, the thing I was showing in the last slide, or even here, like that is the state that we want in the dynamics, and so that's what we're trying to access. So the thing we have to do for the control operation now, when we measure the system, there's going to be something destructive about that because of quantum mechanics, and we can actually take that information from the measurement, feed it back, and to actually achieve this this control operation. This is kind of an inherently non-unitary operation, right? And so there's two kind of transitions which can generically occur in these types of systems. One will be can be in the entanglement related to, as Drew briefly mentioned, the measurement-induced entanglement transitions that can occur. And here I'll be mostly focusing on these control-induced transition or absorbing state transitions. These can actually be measured by an order parameter, whereas for the entangling transitions, you usually need to do some post-selection to find them. So this is the kind of how the phase diagram usually ends up looking like between the measurement-induced phase transition and the control transition. So for some of the dynamics, it actually turns out that the control transition is also an entangling transition, but very generically, it ends up being something a bit more like this, where you have some area law that you're already in. And then after you go to the control side, you do something like disentangle the system, or you go to a well-defined entanglement at the end of the day. If you were to actually make something long-range entangled, this would be like a log 2 with certainty, whereas area law would have more fluctuations in the entanglement associated with it. So the map, the two maps that we'll actually consider are a 1D map, which will be what we put on the IBM quantum computer, and the 2D Arnold cat map. So here I have a picture of my cat undergoing the cat map, which involves a stretching and cutting back together. But first, we're going to focus on the Bernoulli map. So so this is actually what the Bernoulli map is in like very mathematically. It's a phase space between 0 and 1. You have to stretch and then fold it back onto this 0-1 interval. I'm not going to go through the whole details of actually building this onto a quantum computer. I'll just show you what we do on the quantum computer because it already is sufficiently abstracted away from this that you can kind of understand it on its own. So this is what we do on the IBM quantum computer. And so there are two maps. There's this map here, the Bernoulli map, which is just basically a 2-qubit unitary matrix, which is going to mix up the system and put entanglement in. And this will be implemented by some single qubit unitaries and a CZ gate. The reset, and we'll be using for our control operation basically a reset, where you basically measure the system and then you use that outcome to basically set it back to 0. Or if you don't have mid-circuit measurements, you could just do a reset operation itself in the middle of the dynamics. So the thing that makes this special, though, is that whenever you do this Bernoulli map or just this 2-qubit gate, you do them in a staircase where you sort of build them up. So you see here that these are actually one after the other in a staircase fashion. And then whenever you do a control operation, you do it on the last qubit that was acted upon by a gate. And then you kind of shift the register up where the next Bernoulli will happen above it. So you can see, for instance, over here, we do a couple of reset operations, back up the staircase, and then the next 2-qubit gate is where this would be. So this, naturally, we're doing this Bernoulli map with probability 1 minus p, and this with a probability of p. Do you have a question? Yeah. You would get a completely entangled state eventually. It would actually unfold into something that would be approximately the same as a brickwork circuit, and you would just get entanglement flowing through the entire system. It could be R random at the end of the day, or close to it. Yeah, so for the Bernoulli map, there's periodic orbits which are unstable. Here we're actually targeting the 0 point in the phase space, which is basically going to be all zeros for the qubits. So it's a very trivial target state of all zeros. But because it's all zeros, that's why the reset operation works quite well. It's pushing us onto the 0 state. We can measure the magnetization, and on the controlled side, you'll see that you actually get a finite magnetization, and the average of this will go to 1 in the thermodynamic limit. And on the chaotic side, things are getting mixed up by the unitaries so much that the average magnetization will be 0. And at the transition, this actually is just a random walk where you're doing your gates versus your resets. This is just a big random walk on the circuit. And so you will actually get a magnetization of roughly one half, but huge variances as well. Yeah. Right. Yeah. Yeah. So why would I want to do this? So I can tell you specifically what we're trying to do here, which is actually trying to. So the motivation of doing this here is to actually try to see what the quantum fluctuations that we can actually pull out are near the transition itself. So this actually provides a very nice platform for the entangling gates are putting quantum fluctuations into the system. The resets are taking them away, and we can actually use the fact that there's within the dynamics at the transition, there's going to be a whole bunch of pockets of these quantum fluctuations where we can actually then look at them and ask, are they different from just noise, for instance? So that's On the more theoretical side as well, though, we have now here the magnetization is just a observable linear and the density matrix, which captures the phase transition like all by itself, again, without any post selection. The state itself is pretty trivial. It's all zeros, but like you go from something that's more mixed to something that is zeros. Okay, so let's actually linger a little bit on this random walk universality. So this is kind of the picture you should have in your mind. You do the unitaries in sort of a staircase fashion, and this has some entanglement that it sort of drags along with it. If you do enough of these, they'll wrap around and create eventually some multipartite entanglement through the whole system. However, we're interleaving this with these measurements and resets, which are killing the entanglement, but also setting our state to zero, which we can measure. So if we think about what a random walk does and what the universality of this will actually be, we kind of all know that the time scale gives us a z of 2 for some just diffusion. And we can really see that if we take a random walker in some finite space and we ask what happens if we put an absorbing boundary and the random walker hits the boundary and that's the end of the dynamics. Like, how long does that take? That will scale with our dynamic exponent z. And if we start to put some bias into this random walk, represented by p moving away from this pc, then we start to get other exponents like a correlation linked exponent. And if we change our boundary condition to a reflecting wall, or just a hard wall, I should say, then we can ask how long does the random walk stick to the wall? If you're biased, if you're very strongly biased, you'll be hitting the wall and you're just like always trying to like stay on it. This is actually a good order parameter for like the for this transition, and so it'll scale with the size of the system to some power, which will just be 1. So for us, what these correspond to in our dynamics, z, the dynamic exponent, will be extracted more or less from the time dynamics of any observable measurement, whether you're looking at magnetization, if you're looking at some domain wall dynamics, this will be almost in all of those. The beta exponent will be, this will track for how many times you actually hit the wall. And for this, that's whenever a reset hits something that was already reset. So like if you reset things which have already been reset, that is hitting the wall over and over again. And at that point, you've actually quenched all your fluctuations in the system, and you'll see more or less just classical physics just completely take over. Okay. So this is the actual data. The blue here is from the quantum computer itself, where we looked at the average magnetization up to 100 qubits, where we're controlling onto the all zero state. And you actually see that they actually collapse very, very nicely onto some curve, just like we had in the previous slide, but now for the magnetization. And the red dots here are actually the matrix product state simulations. This is all very consistent with the universality that we expect. The new thing we can look at, which is actually not in the classical version of the Bernoulli map, is the fluctuations. So we look at the fluctuations of the magnetization. And so what we do is we fix a circuit realization and we ask what is the, what's like, if we just fix how many times we do the unitaries versus the resets, that circuit realization has a delta mz, just the fluctuations of its own magnetization. And we can now ask, this has a distribution. So we can actually look at the variance of that distribution. So this is actually, in some sense, a variance of a variance. But it's really, we have a distribution of fluctuations. And we want to see kind of if that has some distribution which can distinguish it. And it does. And here, this actually peaks at the transition itself. And I won't talk about the matrix product state behavior here, but you can connect this to some complexity of even the area law phase. So we can also do this for dynamics, and down here you actually see the how the local z operator is changing, and up here again the blue is the actual quantum computer, which collapses and gives us very nicely a z equal to 2, as you'd expect. And you would see the same thing in the variance. All right. So in the interest of time, but what actually is classical? So when I say that we look at these fluctuations of the magnetization, that is partially because of the quantum mechanics we're putting in with our gates. Our gates are entangling; they're creating superpositions, which gives us fluctuations of the magnetization. But if we really wanted to say that we're doing something quantum mechanical, we can't just go and say that this is 0 in our classical map. So we have to think about what would be an equivalent classical thing. And so the equivalent classical thing would more or less be if I have a bath that is constantly measuring my system. I perform a unitary and it just completely measures out my 2 qubits right after this unitary is done. And this will be a very bad quantum computer, right? It just completely destroys the entanglement. It'll be exactly equivalent to a noisy bit machine. And this process here of doing a unitary and then measuring it, this will, if you write this as a quantum channel and do this, this will just be dephasing. You actually get a Markov process that just takes bit strings to other bit strings with some T matrix, which will just be related to the unitaries that you apply to your system. But that's all just completely classical. And that will give you fluctuations on your magnetization. So then the question becomes, are those fluctuations different from the fluctuations we see on the quantum computer? And there, it's, in my opinion, is quite subtle. So here we have both models, both the MPS, which is full quantum, and the dephasing model. And you can see that there's a slight difference in these 2 curves. It's very slight, right? And then the blue is actually the actual quantum computer. And the statement is that the quantum computer is tracking the MPS a little bit better than this dephased model. And we can capture that by actually looking at some KL divergences to see it. In my opinion, it's very, very subtle, but I think a lot of these things, we're looking at Bell inequalities and things like that, are quite subtle on their own, though this might be more so, I fully admit. Doing on time? Great. Okay, so this issue of noise, though, we were putting noise into the system itself with our unitary matrices. We're able to see like all the universality of the random walk. We're able to see like probability distributions of like the fluctuations. But now I want to actually think about what happens if I take a fully quantum chaotic model, something that is truly quantum chaotic. And for that, I'll look at the Arnold cat map. And the nice thing about this model is that it has a 2-dimensional phase space, just like X and P that we learn in quantum mechanics. And what this model does, you should think about the model only existing in this bottom left square, and it stretches the square, cuts it up, and puts it in, sort of folds it back into the square itself. Down here, we have some iterations of the classical version of it where a cherry is getting distorted, and you'll see it reform sometimes. Sometimes it's upside down. And that's because of the finite grid on which this is on that it actually reforms. But in this case, there is classically, there is an unstable fixed point, and that is the point 0, 0. And we can see kind of what happens near 0, 0. If I take a square and I ask what happens to all points on this square due to the cat map, it'll get stretched to this parallelogram. So this is unstable, and that points are getting pushed away from the central point, unless you're on a very specific line. And then we'll apply a control operation, which will more or less take the square and just contract it. So if we do this, classically, you can figure out where the control transition should be. And it's related to lambda, which is basically how much you stretch how much you stretch the square out, and A, which is how much you shrink when you do your control operation. So using that, we can then start to build in quantum mechanics. We have a 2-dimensional phase space. Now our noise can be due to like just the fact that our variables don't commute. X and P. And if you look very close to this point, this will be related to an inverted harmonic oscillator, which is just P squared minus X squared. And we now get for free our Heisenberg uncertainty principle. And this operation, whenever we're doing it to the system, is just a squeezing operation now. So if you try to put your state onto the top of this hill that the inverted harmonic oscillator makes, it'll try to go down the hill, be squeezed. And so that's sort of what happens quantum mechanically now. It's impossible to put it directly on the hill, like the classical case. And for control, it turns out what you have to do the control operation is you bring in a second harmonic oscillator, and you basically do some beam splitting operation, or you have them talk to each other with this interaction where the second qubit, or sorry, the second harmonic oscillator can steal excitations from your first one, which sort of pushes this down to the 0 state, which will be at the top of the hill. And it turns out that this ends up being exactly the same as this classical operation that I showed you before, where we're taking the square and we're just contracting it. This also goes by attenuation. What the full channel of this ends up being. So if we do this, we can. So we're interleaving now these two operations. We're doing the squeezing operation of the inverted harmonic oscillator, and this attenuation, or this taking the second harmonic oscillator, measuring and resetting it. If we do this, we can look at how our fidelity onto the actual 0 state at the top of the inverted harmonic oscillator. And we see that we get a good phase transition at some value here. We've tuned it to be 0.5, and the fidelity ends up being a very good order parameter, which tracks very well, and we get the same universality that we got before, with z equals 2 and beta equals 1. We can formulate this in terms of a covariance matrix, and if you do this, you can even look at the log of the covariance matrix and build a Fokker-Planck analysis, where we can then analytically show that you get all of these power laws that just basically come from the Fokker-Planck analysis of this. But for time, I won't go into much detail there. But then if we bring this back to the cat map, there's one big point that I want to make here, and that's that this compact phase space necessarily gives you a size to your system. And so you have a number of states, which we sort of write as 2 to the L. This naturally leads to an h bar, which is not equal to 1 for us. It's actually equal to this 1 over square root of 2 pi 2 to the L. We have 2 to the L states, and h bar is related to the number of states. This comes from putting a compact map onto a torus. You necessarily have to change h bar to like fit it onto the torus. And so what we get is that this phase transition, whenever we look at this compact map, has to turn into a crossover due to quantum fluctuations, and that's entirely what we see here. So with that, I will just flash up my conclusions, and thank you.
Great. Any questions? So you're taking a cat map that is classical, but you're adding computation onto the operators.
Yeah. Yeah. So we have a 2D dynamical map, and we're basically just saying that each direction has to be like your X and P of like a phase space that we normally are used to.
Yeah.
So can you get a different universality class for the trajectory, like self-avoiding walk, or one of these other things?
Yeah, so it seems like for all of these kind of controller absorbing state transitions, it either becomes directed percolation or this random walk, kind of depending on how you do the dynamics, whether it's the stochastic way or you do the usual directed percolation, where every step you figure out what you're going to do. I'm not aware of other cases, unless you introduce some long range stuff, then you can change the universality. But yeah, I mean the way I think about it, so one thing, most of the states we're looking at here are already like very disentangled, but on top of that, it feels like it should be quite hard to do the control operation fully within the volume law phase, because you're doing measurements and you have to be able to get useful information out of those measurements to then feed back onto the system. And so if you're in your more purified phase where you're actually getting information from your measurements about your state, it's a lot easier to then do your to do your feedback operation and push your state where you want it to be.
Just a pragmatic question. So I thought the IBM machine.
Yeah. Yeah, so I'd say it's so I'd just be more or less trying to like pull from memory what the limiting factor here is, but I think it is just we want to be able to do a lot of these operations, and so like how many qubits can you actually do and still get good time dynamics for like enough time that you saturate this into the phase, because we have to do basically if you have 100 qubits, you have to do like roughly 100 squared operations in order to actually get into the steady state. So I'd say like that's probably the major limiting factor to going larger.